I am Mr. Tarrou. In my third and last video of graphing conic sections in standard form, we're going to take a look at parabolas. We're going to slice these three-dimensional cones in a fashion that is parallel to the edge of those cones. Thus we only get one parabola, as opposed to when we slice these cones parallel to their axis, we get, a pair of hyperbolas. And again, parabolas and hyperbolas are not the same shape. It's not just you have two parabolas stacked on top of each other. They do not have the same shape. As an example, parabolas do not have asymptotes like hyperbolas do. So let's get this screen out of the way and take a look at some of the basic structure of parabolas, and then I'll work through a few examples for you to help you understand how to graph these. The basic structure of parabolas are simpler than those for ellipses and hyperbolas. There's no center because it doesn't have as much symmetry as those graphs do. There's only one vertex as opposed to two. There's only one focus point as opposed to two. And with hyperbolas and ellipses, we need values of A, B, and C. A going from center to vertex, B going from center to the end of the minor axis for an ellipse, or just the distance that's perpendicular to the transverse axis for hyperbola. I'd love to have another name for that non-transverse axis. And then C is the distance between center to focus points. Well, in a parabola, we only have one measurement that we actually are concerned with, or the most important measurement, I guess you could argue too if you want to discuss this unfortunate name of latus rectum, is the distance of P. P is going to be the distance between the vertex and the focus point, and the vertex and the directrix line. There is no A, B, and C, just this distance of P. So a parabola open in a vertical direction, whether it's up or down, those are going to be recognized by identifying that it's the x terms that are being squared, and the y terms are to the first degree. With a sideways or a horizontal parabola, whether it opens right or left, the y terms are going to be squared, and it's going to be the x terms that are to the single degree. And hopefully your textbooks are putting these into the same standard form appearance as my pre-calculus book. I could imagine there may be some small variations here and there, but this is how my book presents them. And this coefficient of 4p that you will find in front of the single degree terms. Well, this distance of 4p is the length of the latus rectum. I wonder if the word rectum had a different meaning back when they came up with this vocab word. So a little bit of an unfortunate name, but latus rectum. It is the length of the line segment that is going through the focus point in a perpendicular fashion to the axis of symmetry, and the length of that is equal to 4p. So if we have an equation of a parabola in standard form, we will be able to look at the h and k values and tell what the vertex is. So the vertex of a parabola is hk, just like h and k is the key point for ellipses and hyperbolas, but it's the center point. So we'll have that point from standard form, and then we'll take 4p, we'll take this numerical value here, we'll set it equal to 4p, we'll divide both sides by 4, and get this measurement of p. And we'll move off the vertex, and one of those movements will get us to the focus point. Perpendicular to that movement, again perpendicular to the axis of symmetry, from that focus point you can go left a distance of 2p and right a distance of 2p, giving you a total length of your latus rectum of 4p, and that'll be an easy way to get two more points to then just draw your parabola through. So this 4p value in the definition of the concept of latus rectum will quickly give you 3 points to draw a reasonably accurate representation of what your parabola is going to look like. Yeah, I think that's all I can say about that. Now over here we have a horizontal parabola, and I've got the diagram a little bit different, drawn a little bit differently for you to show you the relationship of what does the focus and the directrix line do to help draw a parabola. Every point on a parabola, whether it's the vertex and that special distance where these two segments, because it's perpendicular to the directrix line, those two distances are the measurement of P. So from vertex to the graph, and from the graph to the focus point, specifically going through the vertex, those two measurements are equal, and they happen to both be p. But it doesn't matter what point you pick on the parabola. The distance from focus to the graph and the graph to the directrix line are always going to be equal. So if you really wanted to make a nearly perfect or as perfect as you can drawing of a parabola, that's how you do it. Now, why do we care about parabolas? Well, they have a lot of real-life applications. When you throw like a ball or something that doesn't have its own power source to, push it along, that flight path of sort of just a free-falling object, like a football maybe, that path is going to follow a parabolic shape, or at least close enough to use parabolas to model it. Also, all of our satellite dishes, all of our flashlights or headlights that are reflective type, anything that sends or receives signals are going to be in the shape of a parabola, because a property is if this is a light bulb, okay, and we'll get to this again when we get to application word problems for these conic sections. If this were, say, a light bulb and it was emitting energy in the form of light waves, any energy, well, some of it would escape out the front. We don't have like a laser beam because this parabola that's a reflector and a flashlight doesn't go on forever. But any light that does hit the reflector is going to come off, and of course, like you see with a flashlight, come out as a beam of light. So why is it when you use a flashlight, if it's a good one, you get that small little hot spot of light? That's because all the light hitting the parabolic reflector is going to come off in parallel rays. Or if this were a satellite dish and these signals were coming into the parabola, they would all hit that parabolic bowl and be directed towards the focus point. So this could be a receiver for a satellite dish or a microphone, or in the case of like a flashlight where it's emitting energy, all the light waves coming out of that parabola, if it's a perfect parabola, and if the light is right at the focus point, are all going to come out in a parallel fashion. So you can see this would have a lot of real-life applications in the world that we live in. So let's get this erased and start doing some examples. Here we have a parabola in standard form. There is not much to it. So we're going to look at this, and right off the bat, there's nothing with the x and y values, so our vertex is going to be at 0, 0. My y term is squared, so this parabola is either going to open left or right, and since my 4p value here is positive, that's going to tell me that my graph is opening to the right. So let's make a note of that. Let's just give myself a little quick sketch here, just a little like, hey, don't forget, we're going to the right. And 4p is equal to 12, so we're going to divide both sides by 4. And p is equal to 3. So, that being said, if you're not very visual, or maybe I could argue you're more visual because you see this in your head a little better, you could write the vertex, which we have, and then the focus and the directrix. We're going to I'm going to draw it first, make sure I can see really what's going on, and then list off the information. So I have an xy axis here, and I have a vertex at 0, 0, and I know that because my y is squared and 12 is positive, it's going to be going to the right, and my p-value is equal to 3. So I'm going to go from the vertex to the right 3 places, and place, let's just for teaching purposes, put a F here for focus. And then I'm going to go back 3 places, 1, 2, 3, and just temporarily make a little mark. Since my notes, I did my directrix lines in green. Let's go ahead and add that in. So my focus and my directrix, these are not the graph, but they need to be included in the graph when you first take this quiz or chapter test. I'm sure your teacher is going to be looking for these values. And there the distance of 3 is the distance from vertex to focus and vertex to the directrix line. Let's just put a little DIR there. And the parabola, now I can just go and just draw a quick parabola, but 4p is the length of my latus rectum. My latus rectum this perpendicular line segment that's going to be, or this line segment that's going to be perpendicular to my axis of symmetry. My axis of symmetry is horizontal because that's the way my parabola is going to open up, is 12 units long. Let's go ahead and write that down. My latus rectum is equal to 12 units. So from this, I don't want to go up 12 units and down 12 units. The entire length of the segment is 12 units. So we're going to go up 6. So 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. So these are going to be just, that was nice and easy. I didn't have to do a t-table or plot any point, do any arithmetic to find those. I just go up 6, down 6, and that entire length is equal to 12. So now I've got 3 points that my parabola goes through, and it's going to look something like that. So there's my parabola, opening to the right. Let's use this picture to make sure that we accurately write down all of our information. Well, we already have the vertex. That's pretty much all we have. So we have a focus point that is 3, 0. We have a vertical line, which is our directrix. This vertical line, which is our directrix, vertical lines, when you go up and down, you're not changing the x value, you're changing the y value. So the equation of a vertical line is x equals a number. So the directrix is going to be x equals -3. Now, depending on your textbook and what you're being asked to do, you might be asked what the axis of symmetry is. I don't believe my book emphasizes that too much. I forget offhand, actually. But my axis of symmetry the ellipses and hyperbolas have 2 axes of symmetries. They're horizontal and vertical, unless those graphs have been rotated. Let's see here, y equals 0. And I haven't talked about domain and range in a while. So just for review purposes, the domain of this graph, the domain of a graph is all the x values that it uses. This graph starts at 0 and includes 0 and goes to the right forever. So your domain is your x values starting at 0 and going to the right forever. My pre-calculus book uses interval notation or prefer you to use interval notation for domain and range. You might be just saying that the domain is x is greater than or equal to 0. Range, well, those are your y values, and this graph goes up and down forever. So your range is going to go from -infinity to positive infinity. Next example. Woo! Love this stuff. Here we have an example with the x term being squared. So this parabola is either going to open up or down. But let's not make that determination until we have this in standard form. We're going to do that by, we need this leading coefficient to be 1 in front of the squared term. So we're going to divide both sides by 2 and get x minus 3 squared equals 10 divided by 2 is 5. So 5 times y plus 1. So we have the x terms being squared, and the coefficient or the value in front of the single degree binomial, y plus 1, is positive. So this parabola is going to open up. Its vertex is equal to 3 and -1. Let's not forget that the standard form is x minus h squared equals 4p times y minus k. So, these signs in here, the negative signs are already in standard form, so make sure you change those signs as you pull out h and k to find the vertex. Same as when you found the center of circles, ellipses, and hyperbolas. What else do we need to know? We need to know that the latus rectum whose length is equal to the absolute value of 4p is equal to 5, and that 4p, which is equal to 5, will give you a value of p of 5/4 when you divide both sides by 4. So the vertex is going to be 5/4 of a unit away from the focus point and the directrix. So we'll be using that when we get to graphing. And again, at this point, you could draw. You could list off what the vertex is going to be, the focus is going to be, what the directrix is going to be, the axis symmetry, the directrix line, everything like that. I do the pictures first because I'm really more visual. I need to see it. So our vertex is at 3, -1. So 3, -1 is going to be our vertex. Our directrix is going to be 5/4 of a unit away. Just a minute. So anyway, let's get back to it. We have a vertex of 3, -1, and P, which is 5/4, and we have a parabola opening up. So we've got the vertex of 3, -1, and from there we're going to move up, let's see, 5/4, so 1 and change, so put the focus point right there, and go in the opposite direction and do the directrix. So we're going to go down 5/4, or 1 1/4. And, just as a sketch here, there's our directrix line. Okay, directrix lines that are horizontal, or horizontal lines, are in the form of y equals a value. So the directrix is going to be y equals, let's see, we're at this y value of -1 minus 5/4. We need common denominator, so let's get this to be -4/4 by multiplying that fraction on top and bottom by 4. And our directrix line is equal to -9/4, or y equals -9/4. Our lattice rectum is 5 units long, so we're going to go left and right 2.5 units. So let's go 2.5 units to the right and 2.5 units to the left. That's going to give us a parabola that looks something like this. Good enough. Let's see, what else do we want to talk about? We've got the vertex. We've got the directrix. This should be in a nice, neat list. Sorry about this. We have a focus that is at 3 and -1 plus 5/4. So again, you want common denominators here. So that's going to be -4/4. So our focus is going to be 3, and -4 plus 5 is 1/4. Little fraction work never hurt anybody. Vertex, focus, directrix line. If your teacher is concerned about you writing these down, we've got an axis of symmetry. So axis of symmetry, and it's going through, the axis of symmetry now is going through the x-coordinate of the vertex. So it's going to be x equals 3. The vertical lines have the equations of x equal a number. And the domain, just to do a little bit more review again, domain are going to be your x's from -infinity to +infinity, because the graph is going to open up forever. You might be just calling it all real numbers. And the range, which your y values, your smallest y value is -1, and it goes up from there. So your range is going to be your y values, where you go from -1 to +infinity. One more example, and we'll be done. Our last example is also not in standard form, but with our single degree terms of y, we're going to have to complete the square to get this into standard form. So to get your equations into standard form, you're going to have to complete the square. You only do it once because of only one squared term. We're going to get the values that are squared, or the variable that has the exponent of 2 alone on one side and everything else on the other. So we're going to move the 24x over with subtraction and the 50 over with subtraction, because they're already positive, and get 2y squared minus 4y equals -24x minus 50. You cannot complete the square if your leading coefficient is anything other than 1. And because we only have one squared term, we can just simply divide that 2 away from everything that's in the equation before we complete the square, which will simplify it a little bit. So we're going to divide everything or both sides by 2 and get y squared minus 2y. Leave some room for completing the square. This will be negative 12x and negative 25. So completing the square is, again, finding that single degree term. That's b. The coefficient of it is b. So negative 2 divided by 2, square it, and that equals 1. So we're going to add 1 to both sides of the equation. And again, when you do this completing the square step, you are setting up a perfect square trinomial. So to factor this, we only need to square root the first term, square root the last term, and keep that middle sign. So this is going to be y, the square root of y squared is y, minus the square root of 1 is equal to 1. And that you will get a binomial squared. And if you write this off to the side and actually factor it, you'll see that it's y minus 1 times y minus 1. So we have negative 12x minus 24. And my textbook, and like I just showed you a second ago, standard form is that your coefficient of your variables of y and the x must be equal to 1. So before we start worrying about trying to graph this and find out what p is and the latus rectum and what direction it's going in, yada yada yada, we need this coefficient of x to be 1. So we're going to factor out that negative 12 and get y minus 1 squared equals negative 12 divided by negative 12 is equal to 1x. And negative 24 divided by negative 12 is positive 2. Let's see if I can make my list of information a little bit neater this time. That last example got a little bit sloppy. Our vertex is at negative 2, 1. For p is equal to negative 12, so p is going to be equal to negative 3. The latus rectum is the absolute value of 4p. That's what its length is equal to. So it's the absolute value of negative 12, or just 12. Let's get this sketch drawn and get the rest of the information down. And I forgot my x and y axis here, so let's quickly fill that in. Alright, so our vertex, negative 2, 1, so negative 2, 1. Our y term is the one being squared, so it's either going to go open left or right, and with my 4p value being negative 12, my parabola is opening to the left. Again, because of what's being squared, the y, and the sine of my 4p value. So from my vertex of negative 2, 1, my p-value is 3. So I'm going to go left 3 spaces. So 1, 2, 3. And that's going to be my focus point. I'm going to go right 3 spaces. 1, 2, 3. And that's going to be my directrix line, which is going to be x equals 1. My latus rectum is 12 units, so I'm going to go up 6 units and down 6 units, going perpendicular to the axis of symmetry, and my graph looks something like this. Let's see here, vertex, latus rectum, my focus point is 1, 2, 3, 4, negative 5, 1. My directrix is x equals 1. My symmetry line is a horizontal axis, right? going through the focus and the vertex. So a horizontal line that's y equals 1. And the range is, the graph goes up and down forever, so the range, the y values, are all real numbers. And the domain is x is less than or equal to -2. I'm Mr. Tarrou. That's your structure of parabolas, your 3 graphing examples. Bam! Go do your homework.